Welcome back, Concept 53.2. In the next couple of concepts, we're going to look at two different models of population growth. One of them is kind of the idealized perfect world, that would be exponential, and the other one is more of reality, that would be logistic. So first we're going to look at the idealized model. Exponential model describes population growth in an idealized unlimited environment. And this, for the most part, rarely occurs out there in nature in the real world, except for very short amounts of time. Exponential growth doesn't usually occur for unlimited amounts of time, but it does occur in certain instances, and it is a good way to kind of look at and analyze population growth and demography. It's sort of like when you're in physics class and your teacher allows you to discount or ignore the effects of friction. Well, that's not real life, it's not reality, but it does still help us clarify the situation and identify the main concepts. So we can do away with friction when we're first learning the concepts, and then we can get more complicated and add it back in later on. So that's kind of like exponential growth. We are doing away with some of the outside environmental factors that would actually affect this, and taking a look at some of the basic concepts. And again, there's going to be some math involved here, but I want you to make sure and understand that we're looking at the concept and we want to understand the formula and what it means more than try to memorize the formula or anything like that. So it's useful to study population growth in an idealized situation. It helps us understand the carrying capacity, the ability of species, how quickly they can increase their population, what are the conditions necessary for that population growth, and that type of thing. A good example would be, say, if we were to say, look at E. coli bacteria, the E. coli bacteria that live inside your gut. Those bacteria reproduce asexually by dividing in two. They can do that every 20 or 30 minutes. If they were to do that unchecked, if they had an unlimited food supply, unlimited space, and exponential growth were allowed to occur indefinitely in a day and a half, in less than 2 days, in less than 48 hours, there would be a layer 30 centimeters, which is almost 12 inches, almost 1 foot deep, of E. coli bacteria over the entire globe. So as you can see, exponential growth doesn't go unchecked out there in nature. If it did, we would be up to our ears in E. coli bacteria alone. So we'll talk about what exponential growth is, and then we'll kind of get into the real world, which is more logistic growth. Alright, here we go with a little bit of math. Per capita rate of increase. The change in population size is equal to the births plus the immigrants coming in minus the deaths minus the immigrants leaving the population. That's pretty simple, right? So we have to account for all of the new creatures who were either born or came in from somewhere else, and we have to account for all the creatures that either died or left this population and went elsewhere. If we ignore immigration coming in and immigration leaving out, a population's growth rate, the per capita increase, is equal to the birth rate minus the death rate. Pretty simple, so we'll start there with the simple. If we wanted to express that mathematically, this is what we would do. Remember, it's birth rate minus death rate. So B is our birth rate, a number of births, and D is our number of deaths. That is going to equal to the change in, the little delta means change, the change in population size over the change in time, the time interval. So that time interval is usually, if we're looking at population changes, oftentimes it's 1 season or 1 year. But our births minus our deaths would equal our population change over a specific time period. Now, instead of looking at the actual number of births and number of deaths, we might want to generalize and we want to look at an average. So let's look at the average number of births and deaths per individual during that specified time interval. Again, usually a year or a season. So we're going to use B, which is our births, and that's going to equal our annual per capita birth rate. So little b is our annual per capita birth rate. So our births are equal to the annual per capita birth rate times the population size n. So remember, our per capita is how many births per person or per creature. You multiply that by the population size and you would get the total number of births. With death, same way, we use m for mortality, and that's going to be the per capita death rate. How many deaths did we have per person or per creature? Multiply that by the population size, and that gives us our number of deaths. So again, we could write the equation using the per capita numbers. So the per capita birth rate, which would be the per capita, the number of births per individual, minus the per capita death rate, which would be the number of deaths per individual, and that's going to equal again the change in population over a specific time period. The final thing we would need to know is the per capita rate of increase, which is going to be little r, and that's basically just the difference. What is the difference between the per capita birth rate and the per capita death rate? And that's what population ecologists are most interested in. And so this rate determines our population growth. So the little r is the per capita rate of increase. We take the per capita births minus the per capita deaths, mortality here, and that gives us R, which is our rate of increase. And that's what we really want to know. Is it 0, which would be 0 population growth? If the number of births and the number of deaths are equal, well, then you have a static population of 0. If you have more births than deaths, then you have a growing population. And if you have more deaths than births, then you have a shrinking population. So population growth is all about this per capita rate of increase, this little r. That's really what we're actually interested in. And again, 0 population growth is exactly what you would think it would be, where r is equal to 0. If the per capita rate of births is equal to the per capita rate of deaths, well, then you have a population that is static. For every new offspring born, you had an older living creature die. And the number on your population sign didn't change for the year. So one last way that we could write this equation, and again, this would be our change in population over a specific time period, usually again a fixed time interval of a year or a season. That's going to be equal to that ratio of change. Remember, the little r is our per capita rate of increase times the population. So if our per capita rate of increase is 0 times whatever the population number is, well, then our change in population is 0. So this is our rate of change multiplied by the total population, and that would give us our population change over that specific time. If it is higher than 0, if r is higher than 0, well, then the total population increased over time. If r is less than 0, if r is a negative number, well, then your population decreased over that specific time. Now let's use these numbers and these ideas to look at what we call exponential growth. Remember, exponential growth is fairly rare out there in the real world. It may occur for a short amount of time or for certain instances, but it cannot continue unabated, and we're going to discuss why. Exponential growth is listed as R max. So remember, R is your rate of change, the rate of change in the population, and so we just call it R max. It's the population increase under idealized conditions. Under these conditions, the rate of increase is as high as it can be, so we call that R max. Exponential growth means that the population grows at a rate proportional to the size of the population. In other words, as the population grows, the rate of growth also grows. So things get bigger and faster and bigger and faster and bigger and faster. That's what exponential growth is all about. And if you were to look at that on a curve or on a graph, it makes a pretty sharp J-shaped curve. So as the population grows, the rate of growth also goes up, and you end up with this J-shaped curve. So here we have another way of looking at this, or actually just another graph. And this one was in your book, and it just shows again this J-shaped curve, which is exponential growth. The J-shaped curve of exponential growth characterizes some populations out there in the real world, but usually it's only short amounts of time or in certain conditions. Some places out there in the real world where you may see exponential growth would be like in a rebounding population. The example they use in the textbook is in Kruger National Park in South Africa, when they finally banned elephant hunting and they cracked down on poaching. For a short amount of time, there was a J-shaped curve of exponential growth in the elephant population, because you took away all of the enemies, you took away the hunters and the poachers, and so for a short amount of time there was a rebounding population, and where the elephant population had been below what we call the carrying capacity, it rebounded quickly and for a short amount of time had this J-shaped curve, just like you see here. So you can see about in the 1950s and 60s, when hunting was finally banned and poachers were cracked down on, for a short amount of time there was this tremendous growth rate, this exponential curve that you see. Now if we were to take this chart on out, you would see this has not continued along this line, and we'll talk about why coming up in another concept in this chapter. Other places you might see this would be when you bring in invasive species, like when a species is brought from one environment to a new environment. Maybe it has very few competitors or very few enemies in that new environment, and so for a short amount of time it may experience exponential growth and kind of take over this new habitat, and that would be considered a very invasive species. And it does this because it has all the right environmental conditions, it has all the food it needs, but it doesn't have any predators or it doesn't have any competitors, and so for a short amount of time it can go crazy and have this exponential growth. So let's take a break right there. Again, exponential growth is this idealized situation. It does occur in real life, but usually only for short amounts of time and in specific examples that we could talk about. And exponential growth basically just means that as the population increases, the rate of growth is increasing as well. Again, with all the formulas that we looked at just now, I want you to look at them carefully, but you don't want to memorize them. I want you to kind of understand what the letters stand for and what the meaning is behind those letters, but don't worry about memorizing those formulas. I would probably give you those to work with if I asked you this on a test. So we'll take a break and then we'll come back and look at the logistic model, which is more actual reality. Why can this curve not continue forever the way you see it here? We'll be right back.